Now that we have discussed detectors, which identify corners, blobs, and points, let's discuss descriptors, which describe the image region around these points, or corners and blobs. We have already discussed that extrema points extracted from difference of Gaussian images can be used as invariant feature points in an image. For example, in this input image, there are several tiny dots, and these are your extrema points. In order to make these extrema points robust against rotation and lighting, a few additional steps will have to be done. The first step is copies of these feature points will need to be made at various orientations. And the second step is descriptors will need to be extracted around each feature point. So you'll need to describe every one of these feature points using the image characteristics around that point. And in order to make the points invariant to rotation, you have to make copies of these points at various orientations. In order to achieve these goals, we need to compute features around the point. The feature that is described in the 2004 paper by Lowe is to extract gradients around every extrema point or a feature point. For example, we are zooming into a small 8 by 8 area around a feature point located here. At this particular feature point, the gradients are as shown here. At this point, the gradient is 0. At this point, the gradient is pointing in this direction, and its relative strength is as shown by the arrow. The longer the arrow, the stronger is the gradient at that particular point. You would recall that the gradient can be extracted by using Sobel filters. A similar kind of filter setup can be used to extract these gradients as well. Let us see how rotation invariance is achieved from the key points. After obtaining gradients around a key point, a histogram is computed. And this is how the gradient histogram would look like. You have different angles, so each of these gradients have been quantized into one of these angles. And the angles are from 0, 45, 90, 135, 180, 225, 270, and 315. That means all the angles between 0 to 45 are added into this bin. All the locations where the gradient is between 45 to 90, they are inside this bin, and so on. Now within the histogram, there would be one dominant peak and there will be multiple other peaks. The gradient histogram can also be shown like this. For instance, the value of gradient from 0 to 45 degrees is indicated by this arrow. The relative length of this arrow shows the gradient of all the angles between 45 to 90 degrees. And this for gradients from 90 to 135 degrees, that is this particular bar here, and so on. You can notice that the three dominant gradients in this particular image, or this particular region of the image, are from 45 to 90 degrees, 90 to 135, and 135 to 180. So these three peaks. These are the three peaks that we have selected. New sets of key points would be added corresponding to these orientations. Now that we have obtained the gradient histogram and identified the three peaks within the histogram, we will add additional key points for this particular location at the different orientations. So for this key point, which was at location x, y, we would associate an orientation theta with it. The first value of orientation theta would be 45, corresponding to this orientation. So the key point x, y, 45 would be added to this location. Similarly, the other orientation that is added is theta equal to 90. So another key point would be added at the same location with x, y, and theta set to 90. Similarly, the third peak of 135 degree, theta would be set to 135. Now, once we have added the key points at these different orientations, we can compute an oriented gradient histogram by rotating the gradient image to these three orientations. Let us examine how features are extracted for this oriented gradient images. There are three orientations that have been obtained for this particular point. In order to achieve lighting invariance, descriptor windows are selected around the key point, and the window is divided into 16 by 16 arrays and features are computed. This computation of features is done for every one of the orientations. That means it would be done for theta equal to 45, theta equal to 90, and theta equal to 135. As an example, let us see how the features are computed for the orientation theta equal to 90. In the paper, the window was divided into 16 by 16 arrays and features were computed from groups of 4 by 4 such arrays. In this example, we are showing that an 8 by 8 window is selected around the key point. And this 8 by 8 window has been divided into 4 parts. The gradient image is smoothed by applying a Gaussian having a standard deviation equal to 0.5 times the window size. After the Gaussian is smoothed, for each sub-image, that means for each of this block of 4 by 4 pixels, we compute the histogram of gradient magnitude. So a histogram is computed exactly in the same process that we had computed earlier. Earlier we had indicated that the histogram was computed for the entire 8 by 8 region surrounding this key point. Here the histogram of gradients is computed only for a sub-window. So the total number of features that are obtained through the gradient would be 4 into 4 into 8, which is 128. There are 8 directions in the histogram. So you multiply it with 8. While we are showing a 2 by 2 region here, we are showing actually that the number of points that are selected around the key point are 8 by 8 window. In the paper, the region that is selected around the key point is a 16 by 16 window. And this sub-image is not 2 by 2, but it is actually 4 by 4. So because you have 4 by 4 such divisions of a 16 by 16 area, the total number of features that you obtain would be 4 into 4. There are 16 such histograms that you compute, and for each histogram there are 8 angles. So the total number of features are 128. The histogram is then normalized to a unit length, so that all the bins sum to a value equal to 1. Any change in the brightness of the image, that is any change in the brightness of this input image, will uniformly change the histogram. And because the histogram is normalized to unit length, uniform brightness changes will alter the gradient by a constant factor, and when you normalize the histogram, that change in the gradient value will be cancelled out. The normalized histogram that has been obtained from the previous step is thresholded at 0.2. That means any bin in the histogram which is having a value greater than 0.2 is made equal to 0.2. And then the histogram which has been thresholded is normalized once again. This ensures that if there is any bin in the gradient histogram which is having a significant value, that means it's very large, then that bin is truncated and all the other values are normalized to the truncated value. This takes care of non-uniform brightness changes, because any non-uniform brightness change will lead to one of the bins having an inordinately large value, and that is cancelled out by this step. To summarize, extrema points that are extracted from difference of Gaussian images are used as invariant feature point locations. For each of that feature point, multiple orientations are obtained, and copies of the feature points are made at those orientations, and a feature vector is extracted for every feature point and orientation combination. So for example, you can see here that for the feature point 20,157, that is for this location 20,157, there are 3 orientations, 45, 90 and 135. For each of these orientations we have a feature vector. By taking multiple orientations, you are able to achieve rotation invariance. The difference of Gaussians ensures scale invariance. If there are any lighting variations in the input image, that means there is non-uniform lighting on the input image, or there is a brightness change on the light that is incident on the input image, the process of computing the feature vector takes care of it. Thus, the extrema points in combination with the descriptors ensures that we are able to achieve scale invariance, rotation invariance, and lighting invariance. This is an example of a printed circuit board on which some of the key points have been highlighted. You would notice that at some locations there are multiple key points densely placed right next to each other. So for instance, here there are 2 points right over each other. Similarly, many points are present in this region and here. This indicates that multiple feature points are extracted for different orientations. And these dense set of points can be used to match different objects. We have now finished discussion of detectors and descriptors. We will now discuss how the descriptors and detectors can be used to match images. So we will discuss certain feature point matching algorithms. We will look at ransack, which is an algorithm that can be used to match feature points in one image with feature points in another image. The intuition behind ransack is this: given any model f that can be trained on a dataset D, and if we have a loss function or an error metric g that is defined for this model f, ransack selects random subsets of data d1, d2, d3 from the dataset D. So from the large dataset D, you would select random subsets and build models f1, f2, f3 and so on. And the model that gives best accuracy or the best value of loss function g would be selected as the final model. Ransack can be used in the context of any machine learning algorithm. We will use this sample dataset to understand how ransack can be used to select a linear regression model. Subsequent to this, we will discuss how ransack can be used to match feature points of one image with feature points of another image. We will now discuss ransack in the context of building a linear regression model. Given a model f and a dataset D, we expect to know the following. The minimum number of points required to build a model, let's say p number of points are required. In the case of linear regression, this would be 2 points. At bare minimum, you require 2 points to build a linear regression model. You are also expected to know an error metric g, which defines how best a particular point fits a model. K is the number of iterations or the number of models that you want to build. Set f hat to be the best model. This would be an empty model right now, and set the best matching data d hat to an empty data set. And the error value, the best error value that you have obtained so far, as v hat, and this is set to infinity. You also select a manual threshold that would be between 0 to 1. The threshold might have a different value depending on the error metric g. We will go through the rest of the steps using linear regression and this dataset as an example. So the next step is to select p samples randomly from the dataset D and build a model f. In the case of linear regression, we need 2 samples at minimum to build the model. So these 2 are the samples which have been selected, and this line is the model that has been constructed using these 2 samples. Once the model has been built, an empty dataset D dot is created and an error value V dot is set to 0. Notice that this model has been built using only 2 samples, these 2 random samples. In step 4, we loop through all the elements in the dataset. That means we loop through all the elements in this large dataset and select those elements which fit the model within a certain threshold. That means if the error metric of a sample with respect to this line is within a certain threshold, that particular sample would be added to the dataset D dot, and the error of that sample would be added to this value V dot. This highlighted area around the line represents all the points which will be within this threshold. So for instance, this point, this point, this point, this point, and these points are within a certain threshold of this line. So all these points would be added to D dot, and their corresponding error measures will be added to V dot. If the number of samples in D dot is greater than the number of samples present in D hat, which was this best match data set, then we set f hat to f. That is, f hat is set to the current model that has been constructed, D hat is set to the current data set that is available, and V hat is set to the current value of V dot, or the current value of error measures. the variable k is decremented to reduce the number of iterations. If k is not equal to 0, the process is repeated. That means step 2 to 6 is repeated for k number of iterations. Because this is the first iteration of ransack, d hat, f hat and v hat were initially empty. And after this loop is completed, d hat, f hat and v hat would be set to the values corresponding to this model. In the second iteration of ransack, these two were the random points that got picked up, and this orange colored model is fit to the data. Given this orange colored model, the threshold region corresponds to this area, the shaded area, and these are the points that fall within this threshold. Out of the entire data set, 10 points fall within this shaded area. In the previous model, there were lesser number of points in this shaded area. Therefore, this model will be picked up over the previous model that was found. Let's see what happens in the next iteration of ransack. In this iteration of ransack, these are the two random points that have been picked, and this orange line fits the two random points. Given this line, the threshold area is this region. There are only 4 points that fall inside this threshold area, and we may also want to consider this point which is barely touching the threshold area. Let's say even if we consider this point, there are only 5 points that fall within this threshold region. These are lesser than the number of points in the previous threshold region. For the previous model, there were 10 points in the threshold region. Therefore, this model is ignored according to rule number 5. In this iteration of ransack, these 2 points happen to be the random points that are picked, and this orange line fits these 2 points. The overlapping area is this, and we can see that a large number of points in the dataset are falling in this threshold area or the overlapping area. This model now becomes d hat and replaces the older d hat. And as we continue these iterations, we may get different models. If any model turns out to be better than this, or if any other model turns out to fit larger number of points than this model, then that model will be picked up. In this example, we have discussed how ransack can be used to find a linear regression model. By altering the functions f and g, this function f and the function g, we can fit any other model to any other kind of data set. For instance, we can also perform matches between feature points of 2 images. Before using ransack to match the feature points of 2 images, we have to perform outlier rejection. Outlier rejection is the process of selecting an initial set of matching points between the 2 images. Let us say that this is our reference image and this is our target image. For both of these images, you would have already computed feature points and the corresponding feature vectors. For instance, in the reference image, you would have obtained this table which contains the x, y coordinate of each feature point, the orientation of the feature point, and the corresponding feature vector. The feature vectors describe the image region surrounding that feature point. Similarly, for this image, this would be the feature point table and the feature vector. Some of the feature points could be repeated with multiple values of theta. So for instance, this particular feature point 20,157 has 3 orientations. Similarly, in the test image, this feature point 38,192 has 2 orientations, whereas this feature point has only 1 orientation. So every xy coordinate which corresponds to a feature point might have multiple orientations and multiple feature vectors associated with it. This will happen both in the reference image and the target image. We also have defined a sum of squared distance measure which is defined over the feature vectors. For instance, if you are comparing 2 feature vectors from this table, let's say you are comparing this feature vector with this first feature vector, the sum of squared distance between them is computed in the following manner. Each column, for example, you would do 0.15 minus 0.14 the whole squared plus 0.20 minus 0.19 the whole squared, and so on for all the 128 values. Given the set of feature points and feature vectors from the reference image and the data from the target image and the sum of squared distance measure, the outlier rejection is performed in the following way. We would loop through all points in the reference image and compare them with the target image. So for instance, let's say we select this particular point. For this point, to determine which of the points in the target image is the closest, we compute sum of square distances using this function for this feature vector, for the feature vector corresponding to this point, with all the feature vectors in the target image. And we store that in these two values. For instance, if we have 2000 points in this test image, you would compare the feature vector of this point with all these 2000 samples. You would sort the sum of square distances in increasing order. The lowest distance would be stored in 1nn, and the second lowest distance would be stored in 2nn. After the 1nn and 2nn distances are computed for each point in the reference image, we retain those pairs of points that have a low value of the ratio 1nn divided by 2nn. For example, let's say this point was matched with all of these points, and we found that the closest match was with B1. So for instance, point A matched with B1 and gave you the distance 1nn. That means A and B1 were the closest in terms of the sum of square distances. Similarly, if A and B2 had the second closest distance with respect to sum of square distances, that would be the 2nn distance. If the ratio of 1nn and 2nn is less than a certain threshold, then you retain the point A and B1. For instance, the coordinate of A, which is 20,157, and the coordinate of B1, which is 38,192, has been added to this table, and their ratio of 1nn by 2nn is also added to the table. For some other points, let's say for example this point is matching with these 2 points. Let's say this was your reference point that you had selected in the reference image, and it happened to match with this point and have the closest distance. That means the 1nn was the distance between these 2 points, and 2nn was the distance between these 2 points. Then you would add them also to the table. For instance, this is the point 10,68, and this is the point 47,112, and the 1nn divided by 2nn ratio is 1.56, and so on and so forth for other points. For instance, there's a point 10,79 which happens to match with 47,118, and the 1nn divided by 2nn ratio is 1.20. Similarly, this point is 26,58, and it matches with the point 41,120 with a 1nn divided by 2nn ratio of 0.34. Now within this table, we will only select those points which have a ratio that is less than a certain threshold. So let's say our threshold is 0.5, we would select only these 2 pairs of points, the first one and the fourth one. In general, when you compare a reference image with a target image, about 10 to 20% of the points in the reference and the target are picked up in this table. That is, about 20% of the points will have a 1nn by 2nn ratio which is less than a threshold, and these are retained for the next step. In the next step, we use ransack to determine how these points in the reference image can be geometrically mapped to points in the test image. Notice that in the outlier elimination stage, we have determined that point number 20,157 corresponds to 38,192, but this correspondence has been measured using image similarity. We measured the feature similarity using the sum of square differences. This still does not mean that we can take point 20,157 and directly place it on point 38,192. Geometrically, these 2 points are at different coordinates. Similarly, we have established that point 26,58 is similar to point 41,120, but this similarity is using the image matching. We still cannot place 26,58 directly on top of point 41,120. In order to find out how the reference points match the test points geometrically, we have to solve for this homography, where UA are the set of points in the reference image, and UB, indicated by these points, are points in the test image, and H will give you the transformation from the reference points to the test points. A few other points to be noted. image matching might still give you erroneous matches. That means all the reference and the test points mentioned here may not be perfect matches. Some of them might be wrong. And many of these points would be repeated as well because we were selecting multiple orientations. And you'll have hundreds of such points. So given that you have hundreds of reference points matching with test points, where some of them could be repetitions and some of them could be even erroneous, how do you come up with the best homography matrix? The ransack method is used to come up with the homography matrix given these sets of points. In the ransack method, we have the set of selected points in the reference image, which we call as A, and the set of selected points in the target image, which are the set of points in B. The dataset D would be made of all of these points. The number of points that have to be selected in random to compute this homography is 4 points from each image. So you need 4 points from the set A and 4 points from the set B to compute this homography matrix. We can use either affine transformation or non-affine homography as a model. This would transform the x and y coordinates from this set UA to the coordinates in set B. The error metric would be the correctness of homography. That is, once you get the homography matrix and you are able to determine how to take a point in the reference image and place it on top of the test image, if you take the homography matrix and apply it on top of the test images, test points, you should get the original reference points back. That means if you take the homography matrix and you apply it on point 38,192, you should ideally get 20,197. Similarly, if you use the homography matrix, apply it on point 41,120, you should get 26,58 back, and so on and so forth for all the points in your test dataset. This can be computed using the error metric. We have earlier discussed how ransack can be used to search for the best possible model or a linear regression model that could fit this data by selecting random points and finding how many of the other samples agree with the model that has been fitted to these random points. The same process is now applied to find the homography. For instance, if these sets of points were picked up randomly by a ransack algorithm, for instance, these two sets of points, these 2 points, and so on, then they would give a good homography. So these are our correspondences. Using these correspondences, the homography matrix that we obtain will ensure that many other points in the reference image will be very close to the test points that we identified earlier in the table. That means this homography is good. The correspondences picked up from the table may not always give very good homographies. For instance, let's say these were the 4 points that were randomly picked from the correspondences obtained after outlier elimination. Let us say this was one of the correspondences. That means this is a point in the reference image which is matching with this point in the test image. This point in the reference image is matching with this point in the test image according to the image properties. That means these are the correspondences that were present in the outlier elimination table. Using these correspondences, if you come up with a homography matrix, that homography matrix would not be geometrically consistent. Even visually looking at the correspondences will tell you that maybe it's possible that there is some image matching between these points. But if you consider their geometric coordinates, these points do not reflect a good geometric match. The resulting homography will also therefore give random matches. If you applied the homography matrix on top of these test points, you would get erroneous results. For instance, if you took this test point location and you applied the homography matrix on it, it would match up to this point. It would result in getting these coordinates. Obviously, these coordinates on the reference image do not match up with this point. Similarly, if you took this point in the test image and you applied the homography matrix obtained from these correspondences, these 4 correspondences, it would result in this coordinate. Obviously, this coordinate in the reference image does not match with this coordinate in the test image. Similarly, this point in the test image, if you applied the homography matrix on top of this point, you would result in this coordinate in the reference image, which is also a bad match. RANSAC allows you to identify an optimal homography. That is, a homography which allows a maximum number of points in the test image to match up with points in the reference image. This will allow you to overlay the test image accurately on top of the reference image. This is very useful from an application standpoint because now you can take an input image and determine if that input image is located within another input image. For instance, here we have found significant number of matches between this image and this region of the test image. This allows us to determine that this particular image is present at this location. This example shows how RANSAC and feature point extraction can be useful in matching up two different bills and identifying certain regions of the bill. For example, let's say you have a telephone bill on which you know where the telephone number and the amount is located. And this is a bill that you received in the mail, and you want to identify the telephone number and the bill amount in this bill. Using RANSAC and feature point extraction, you can extract feature points from the reference image and feature points from the test image and match up those feature points. Once a geometric correspondence is found, you can then determine this particular amount field, where is it located within the test image. This slide shows an example of feature point matching for image stitching. You have several images here that are stitched to create a panorama. Feature point matching along with RANSAC can be used to determine where are the regions of overlap between these images. And once you get the coordinates corresponding to the regions of overlap, you can stitch them together. Ditto with this image, where 20 images have been stitched together to create a single panorama. Feature point matching also has several applications in areas like medical imaging. In medical imaging, the problem is more challenging because the objects are non-rigid. For example, in the previous case, the objects that you're seeing here, let's say a mountain or a church, these are all rigid objects, they don't move. Whereas in this case, the patient who is undergoing an MRI or a CT might move while the CT is being taken. While this kind of registration is outside the scope of our discussion, it is useful to note that non-rigid registration techniques are also available. These consider individual body parts and model their motion in order to match images together. While an initial match between images is obtained using feature point matching, local matches are also done using the motion properties of individual body parts like the vertebral columns. Once this is done, accurate geometrical mapping of one image to the other can be done. To summarize, we have discussed corner point extraction, blob extraction, and multi-resolution feature point extraction. Some of these extraction techniques are invariant to lighting, some of them are invariant to scale, and some of them are invariant only to rotation. Using these points and feature descriptors, we have studied how RANSAC can be used to obtain geometric correspondence between reference images and target or test images. We have also discussed a few applications of these techniques. Thanks everyone. Hope you enjoyed the lecture, and I will look forward to seeing you in the next class. Enjoy and have fun.